So far in lecture, when calculating electric fields, we've done so for point charges. What about distributions of charge? So let me begin by briefly taking you through the process of how we set up and evaluate ultimately Coulomb's law for distributions of charge. So let's say, for example, that I just start with three-dimensional space like so, and then I have some object, a distribution of charge, for example, like this. Okay, and then right here on the diagram we'll say is our point P, and we want to find the electric field at point P due to this green distribution of charge. Here's then how we go about setting this up. Okay, first of all, right here is an infinitesimally small amount of charge associated with this green distribution. I'm going to call this dq prime. And then relative to the origin, it has a position vector here on my diagram, r prime. Okay, and then little r goes from the origin to point P, like so. And then lastly, capital R goes from dq prime to point P, like so. Such that, once again, we see the exact same tail-to-tip method of vector addition. That is r prime plus capital R is equal to little r. So capital R is r minus r prime. Okay, now what I can do here at point P is find the infinitesimally small electric field that is due to this infinitesimally small amount of charge dq prime by just writing the following. So the infinitesimally small electric field is ultimately then going to be this expression. And then to get the overall or net electric field at point P, then of course what we would have to do is integrate over the charge dq prime to pick up basically the entire distribution of charge. So then therefore we end up with an integral expression. That's this expression right here. And then what we have to do is learn how to set up and evaluate this expression for a couple of distributions of charge. Okay, so let's go ahead and take a look at that first distribution. Okay, I have the problem written out as an example. Okay, what we have here is the infinite line of charge. An infinite line of charge has a linear charge density lambda. That's the Greek character lambda. Charge density is charge divided by volume for a three-dimensional object, charge divided by area for two-dimensional, and in this case, one-dimensional, it's charge divided by length. So the charge density, as it's called, in this case, the linear density, lambda is equal to charge divided by length. Okay, so an infinite line of charge has a linear charge density lambda. Find the electric field at distance z away from the line of charge. Okay, so just to give you some context here, basically all that we have in this situation is a wire. So electrical current is not flowing in the wire. What happens when that occurs we'll get to much later on. But for now, just think of an infinite line of charge, just for context, as a wire. Okay, let me go ahead then and draw on a diagram like so, where here's the x-axis, the y-axis, and the z-axis, and then I'll place the wire here along the x-axis. That is like this. And it's infinite in extent in both directions. Okay, and then right here we'll say is our point P that's being referenced in the problem is the distance z away from the wire, like so. Okay, and then at this point we go ahead and set up our position vectors. So the first thing to take a look at is right here. This is the position vector small r. And I'm going to go ahead and write small r here very simply as just being equal to zk hat. Okay, now right here is the infinitesimally small amount of charge, dq prime. It has a length associated with it, dx. And then right here on my diagram like so is the position vector r prime. I'm going to go ahead and just write r prime here as an xi hat. It doesn't matter if it's on the positive or negative side of the axis. Okay, and then lastly is the capital R vector right here. The capital R vector, you'll notice, forms the hypotenuse of a right triangle. The right angle associated with that right triangle is right here. Notice how I drew that right angle, by the way, where this line here is parallel to the x-axis and this line here is parallel to the z-axis, okay? Okay, now let's go ahead and write capital R prime, or capital R rather. So capital R is r minus r prime. So then therefore that's equal to zk hat, this is k hat here, zk hat minus x I hat. So, however, it is just the hypotenuse of a right triangle, so then therefore if we use a little bit of Pythagorean theorem, the magnitude of r is then therefore equal to, I'll write it as x squared plus z squared to the 1/2 power. Okay, now we need also our infinitesimally small amount of charge dq prime. This is where the density comes into play. So we're going to write the density as the charge divided by the length. Recall that the length of dq prime here is dx. So then therefore the charge dq prime is equal to lambda times dx. Okay, and now I've got everything that I need. We plug everything into the expression. So let's go ahead and do so. Okay, so the electric field then is then therefore the following. Okay, I'm going to write k times r first. So k times capital R vector, and that's this guy right here. Okay, and then multiply by dq prime, like so. And then divide by the magnitude here of capital R cubed. Like so. Okay, now the variable that we're integrating over is x. So then therefore we have infinitely large limits. We are integrating from negative infinity to positive infinity here along the x-axis. So then therefore, how do I ultimately set up and evaluate this integral with these infinite limits? Well, as I said earlier, right here on the diagram is a right triangle. Let's go ahead and take advantage of that by doing the following. Let me define an angle here on the diagram. Let's call this angle theta. And now what I'm going to do is I'm going to switch variables. Specifically, we're going to use here trigonometric substitution to set up and evaluate this integral. Okay, now for the calculation, let's take a look at the I hat integral first. The I hat integral is along the x direction. What would we expect to find about the x component of the electric field at point P for this infinitely long wire? What we should end up with is 0 in the x direction by symmetry. Think of it like this. So this little dq prime right here is ultimately going to cause an electric field at point P that kind of points in that direction like so. Okay, this guy's symmetrical counterpart on the other side of the diagram is going to cause an electric field at point P that points in this direction like so. What we should find is that the x components of those two little vectors that I'm pantomiming here should cancel each other out. So then therefore let's take a look and see what happens with the I hat integral. Okay, now let me write the integral itself before we do this trigonometric substitution. So I'm going to have here k and then x I hat lambda. K x I hat lambda, and then multiplied by dx. And then divide them right here by the denominator. Okay, I haven't switched variables yet, so we're integrating from negative infinity to positive infinity. Okay, now specifically the trigonometric substitution. What do we do here? The key is understanding the Pythagorean theorem here in the denominator of the expression. What we're going to do is we're going to write on the diagram above the tangent of the angle theta. Okay, now the tangent of the angle theta is equal to the opposite side, which remember is x in terms of magnitude, divided by the adjacent side, which is z. Okay, let's go ahead and solve for x, which is the variable that we need. So that's z tangent theta. And then let's go ahead and differentiate. When we do, we get z secant squared theta d theta, like so. And now let's go ahead and switch variables here for our integral. Okay, so setting this up. Okay, first of all, let's see the constants. We have k times lambda times I hat, like so. And then I have here x times dx. Okay, the x is now z tangent theta, like so. And the dx right here is z secant squared theta d theta. Okay, and then we have our denominator, like so. So we have x squared, so that's going to be z squared tangent squared theta plus z squared, all to the 3/2 power, like so. Okay, now, what are the limits of integration? Why did I bother to do all of this, for example, as I said earlier, in trying to deal with these infinitely large limits when talking about the x direction? Well, take a look at the lower limit of integration, negative infinity. So negative infinity on the diagram above is way out in this direction like so. What does the angle theta correspond to at negative infinity? It corresponds to negative 90 degrees, negative pi over 2. Think of it like this. So right here on this diagram, if I use this stick here to illustrate, right here is the angle theta. And then watch what happens with the angle theta when I start to move the stick out to infinity, the edge of the stick rather, like so. Notice that the angle theta more and more approaches a 90-degree angle, and we are in this case going in the negative direction. So then therefore we're going to integrate from negative pi over 2 to positive pi over 2 like so on the positive side here of the z-axis. Okay, so let's go ahead and write those limits. So negative pi over 2 to positive pi over 2 like so. Okay, let me do some erasing here. I'm going to need some room, obviously. Okay, and then I have right here what initially looks like a huge mess. However, as you'll see, this actually reduces quite nicely. So let's go ahead and start simplifying. Okay, first of all, in the numerator, I've got k lambda I hat. Like so, I've got a z squared. We've got tangent times secant squared. Now, specifically in the denominator, let's go ahead and take the z squared here and factor it out from each term. When I do, I factor it out, and then I have to take the square root of it, so it becomes z, and then I have to cube it, so it becomes z cubed. Like so. And then here's what's left. I'll put it in brackets. Tangent squared theta plus 1, all to the 3/2 power. You may recognize tangent squared theta plus 1 as a trigonometric identity. Specifically, it's secant squared. So now let's go ahead and rewrite this. So integral, negative pi over 2 to positive pi over 2. Okay, let's get rid of some of the constants here. This z squared is going to cancel over the z squared here. And then I can start to pull things out in front. K lambda I hat over z squared, or over z, excuse me. So k lambda I hat over z, there we go. Okay, tangent times secant squared, d theta, and then divided by the following. Secant squared, take the square root of it, is secant. Cube it, secant cubed. Like so. Okay, simplify further. A secant squared cancels out with a secant squared like so. And then we're left with the following. Okay, let me go ahead and pull these constants out. K lambda I hat over z. Integral, negative pi over 2 to positive pi over 2. And now we have the following. Tangent of theta is sine over cosine. Secant of theta is 1 over cosine. The cosines cancel and you're left with sine. Like so. Okay, what is the integral of sine? Well, the integral of sine is negative cosine. Derivative of cosine is negative sine of theta, so then therefore the integral of sine is negative cosine of theta. Like so. But then take a look at what happens then when we plug in our limits of integration. We're going to have here negative cosine of pi over 2. Well, cosine of 90 degrees is 0. And then similarly, cosine of a negative pi over 2, cosine of negative 90 degrees is also 0. So ultimately, this is all just equal to 0. Like so, as we expected earlier. So yes, as we expected earlier, by symmetry, the x components of the electric field at point P on the diagram above do in fact cancel out. They all add up to 0. Okay, so then where am I at this point after all of that? Well, let's go ahead and erase. And then if we jump back up to here, we already know that the I hat integral is gone. The I hat integral is equal to 0. And so then therefore this right here now becomes this. Okay, first of all, we've got k times lambda, and then multiply by zk hat, then times dx, and then divided by our denominator. Like so. Okay, and then once again we make the exact same trigonometric substitution as I did earlier. Okay, so that begins in the following way. Tangent of theta once again is equal to x over z. Therefore x is equal to z tangent theta. Therefore dx is equal to z secant squared theta d theta. Like so. Okay, let's go ahead and switch the limits then as well. So now we're integrating from negative pi over 2 to positive pi over 2. Okay, and then we've got, first of all, k lambda z k hat. Then times dx, which is right there. Like so. Okay, and then divided by right here, z squared tangent squared theta plus z squared, all to the 3/2. Okay, and then we have to simplify this mess as well. So when we simplify this mess, basically we run through the exact same series of steps as I did earlier when talking about the I hat integral. In this case, however, it doesn't simplify all the way down to 0. Okay, so let's go ahead and begin that process. So take a look at the denominator first. I'm going to factor out a z squared here from each term. Then I'm going to go ahead and take the square root of it, which becomes a z, and then cube it, which becomes z cubed. Okay, so first of all, I've got k lambda zk hat times z, so z squared. So k lambda z squared k hat, and then times secant squared theta d theta, all divided by then z cubed, tangent squared theta plus 1, all to the 3/2. Like so. Okay, a z squared cancels here and here. We have a z that is left behind. Okay, let me go ahead and do some erasing here. Let's get rid of all of this. Okay, and then here's what's left. Okay, so k lambda k hat over z. Okay, now let's go ahead and start simplifying here the trig terms. So tangent squared plus 1 is once again secant squared. Take the square root of it, so it becomes secant. Cube it, so it becomes secant cubed. And then we have secant squared over secant cubed, which is 1 over secant, which is cosine. So ultimately, this trigonometric mess here, if you will, just becomes cosine. Like so. So once again, let's check that. Tangent squared plus 1 is secant squared. Take the square root of it, it becomes secant. Cube it, it becomes secant cubed. Secant squared over secant cubed is 1 over secant, which is the same thing as cosine. Okay? Okay, so now let's go ahead and finish up. All right, so integral of cosine is sine. So k lambda k hat over z, sine of theta, from negative pi over 2 to positive pi over 2. Okay, so doing the brackets here carefully. We have here, first of all, sine of pi over 2, which is 1, minus then sine of negative pi over 2, which is negative 1. Like so. This then, of course, ends up being 2 in the brackets. Like so. And then we end up with the following as our answer. Now, as you can see, it took me the better part of 20 minutes or so to set up and run through the evaluation of this complicated integral to ultimately arrive at this result. A little bit later on, when we get to the next chapter, when we get a little bit more fundamental with what exactly is being said by Coulomb's law, I'll actually do the exact same problem again, but in that case, it'll only take me a couple of steps and it'll just take less than 5 minutes. But we'll get to that a little bit later on. For now, however, let's just look at the result. So when we look at the result, notice that as you get further and further away from the infinite line of charge, the magnitude of the electric field does not drop off as an inverse square law distance. That is, it doesn't look like a 1 over distance squared relationship. In this case, it's a 1 over distance relationship, like so, as opposed to 1 over distance squared. But the magnitude does decrease according to this relationship here. And then the direction of the magnetic field, or excuse me, of the electric field lines, is that the electric field lines are all perpendicular to the wire itself, and they are radially outwards from the wire. That then looks something like this. So let's say right here is the wire on the diagram above, and then let's just pick some individual points, say here, here, and here. And then perpendicular to the wire and radially outwards from the wire are all of the electric field lines. So right here in this position, we've got the electric field lines like so. In this position, the electric field lines like so. As I draw this diagram, you have to kind of start to think three-dimensionally. And then same thing at this point, the electric field lines like so. One of the things that I've posted for you is a screencast that shows an applet. In that applet, we can then, in 3 dimensions, actually render what these electric field lines look like, okay? Okay, so that's the infinite line of charge calculation. Once again, for context, it's basically the electric field due to a wire.